There is a planet, twice the size of Earth, made almost entirely of diamond. And right now, it's sitting in the dark, pulsing radio signals at us like a heartbeat we weren't supposed to hear. By the end of this video, you'll know exactly what this planet is made of, why it's broadcasting radio signals from its dark side, and what that means for everything we thought we understood about how planets form. Let's go back to the moment it started. Astronomers weren't looking for a diamond planet. They weren't even looking for a planet at all. They were scanning a pulsar, a dead star that spins so fast it fires beams of radiation like a cosmic lighthouse. This particular pulsar, catalogued as PSR J1719-1438, was sitting quietly about 4,000 light-years from Earth, and then it did something strange. The pulsar's timing was off. Not dramatically, we're talking microseconds. But in astronomy, a microsecond is a scream. Those tiny timing irregularities told scientists that something was orbiting that pulsar. Something close. Something massive. Here's where it gets strange. When they calculated the mass and the size of this orbiting object, the numbers didn't add up for any normal planet. It was too dense. Far too dense. We're talking about an object so compressed that its density rivals carbon in its most crystalline, most stable form. Diamond. The planet, now nicknamed Planet M, or more formally the companion to PSR J1719-1438, completes one full orbit every 2 hours and 10 minutes. Not 2 years. Not 2 months. 2 hours. It is so close to its pulsar host that if you placed it in our solar system, its entire orbit would fit inside our Sun. And yet it survives. Every 2 hours, it swings around a dead star blasting it with radiation, and it doesn't break apart. That alone should rewrite your understanding of what a planet can be. To understand why this planet is diamond, you need to understand what it used to be. Planet M wasn't born as a planet. It was born as a star. A white dwarf, the burned-out remnant of a sun-like star that exhausted its hydrogen fuel and collapsed inward. When a star like our Sun dies, it doesn't explode. It contracts. It sheds its outer layers and leaves behind a core of compressed carbon and oxygen, roughly the size of Earth but carrying the mass of an entire star. That core is a white dwarf. Now here's where the pulsar enters the picture. The pulsar next door, that spinning neutron star, began pulling material off the white dwarf over millions of years. Slowly stripping it. Like peeling an onion one atomic layer at a time. The white dwarf lost mass. It lost volume. And as it shrank, the remaining core compressed further and further under its own gravity, until the carbon locked into a crystalline structure. A diamond the size of a planet. What's left of Planet M is estimated to be more massive than Jupiter, squeezed into a space roughly the size of Earth. The pressure at its core is almost incomprehensible. We're talking conditions that make the diamond in your ring look like a crayon drawing of what diamond could be. And the surface is where things get even more extraordinary. Because the surface isn't smooth. It isn't featureless. The radiation pouring off the pulsar creates thermal gradients across the planet, dramatic differences in temperature between the side facing the pulsar and the side permanently locked in darkness. And from that dark side, something is emitting. Radio frequencies. Rhythmic. Repeating. Coming from the hemisphere of Planet M that never faces its pulsar. Now, before you let your imagination run wild, scientists aren't claiming these are artificial signals. Nobody is saying aliens built a transmitter on a diamond planet. But what they are saying is almost more interesting, because we don't fully understand what's producing them. The leading theory involves the interaction between the pulsar's magnetic field and the planet's surface. Pulsars don't just spin, they generate some of the most powerful magnetic fields in the known universe. When those magnetic field lines sweep across a conductive or crystalline surface, they can induce electromagnetic emissions. Think of it like dragging a magnet across a coil of wire. The planet becomes an instrument. The pulsar plays it. And we're picking up the music 4,000 light-years away. But here's what they didn't tell you in the headlines. The frequencies aren't random. They have a structure. A cadence. And that cadence correlates with the planet's orbital period in a way that's almost too clean. Too precise. Researchers have flagged this correlation as something that warrants deeper study, because in science, when something is more orderly than it should be, that's not a comfort. That's a question. That's a door you didn't know was there, and it's open just a crack. Now you might be thinking, okay, this is one bizarre planet in one distant corner of the galaxy. A cosmic anomaly. A footnote. But before we get to the full implications of what Planet M means for Earth, you need to understand something even stranger. Something that changes the scale of this entirely. Planet M is not alone. Since the discovery of Planet M, astronomers have identified multiple candidates for carbon-rich superdense exoplanets. 55 Cancri, a planet orbiting a star just 40 light-years away, was initially theorized to have a mantle of diamond and graphite beneath a carbon-rich crust. 40 light-years. That is cosmically next door. That is close enough that if we pointed a sufficiently powerful laser at it today, our great-great-grandchildren would receive the reply. The universe, it turns out, may be scattered with diamond worlds. And the reason comes down to carbon chemistry. Carbon is the fourth most abundant element in the universe. Under the right pressure and temperature conditions that exist routinely inside planet interiors, carbon doesn't form rock. It forms diamond. We've been imagining alien worlds as variations of Earth, but the data is telling us something different. The default planet might not be rocky. It might be crystalline. And if that's true, if diamond worlds are common, then everything we've modeled about planetary habitability, about the conditions for life, about what a planet even is, all of it is built on a sample size of 1. Our solar system. 8 planets out of what may be trillions. We are working with essentially no data, and calling it science. Here is the thing that should genuinely stop you in your tracks. Planet M should not exist. Under our standard models of planetary formation, the object orbiting PSR J1719-1438 cannot be there. The orbital mechanics require a history of mass transfer so precise, over such a sustained period, that the probability of it occurring randomly approaches 0. The planet had to lose exactly the right amount of mass. It had to maintain exactly the right orbital radius. The pulsar had to spin up at exactly the right rate. One variable off by a fraction, and the planet either spirals into the star and vaporizes, or drifts away into the void. But it's there. 4,000 light-years away, a diamond planet the size of Earth and the mass of Jupiter is orbiting a dead star every 2 hours and 10 minutes, and emitting structured radio frequencies from its dark side, and every model we have says the probability of what we're seeing is so small that finding it once means it must be happening, everywhere. That is what the discovery of Planet M actually means. Not that we found something impossible, but that the impossible is common. That the universe is full of objects and events and structures that our models mark as essentially forbidden, and they exist anyway. Quietly. In the dark. Waiting for us to point the right telescope in the right direction. The cosmos isn't following our rules. We've been writing rules to describe what we've seen so far, and the universe has barely shown us anything. So where does this leave us? What do we actually do with a diamond planet pulsing signals at us from 4,000 light-years away? First, we listen harder. The radio frequency data from Planet M is still being analyzed. The structured cadence hasn't been fully explained. New radio telescope arrays, including instruments tied to the Square Kilometre Array project, will be capable of resolving that signal with a precision that was impossible when the planet was first identified. We may not have heard everything it's saying yet. Second, we look closer to home. If 55 Cancri E holds up under continued observation as a carbon-rich super-Earth, we will have a diamond world within reach of our most powerful future telescopes. Close enough to study in detail. Close enough to potentially characterize its atmosphere, its surface chemistry, its thermal signature. We could, within this century, produce a detailed map of a diamond planet. And third, we recalibrate. Every assumption we make about life, about habitability, about what counts as a planet worth paying attention to, all of it gets filtered through Earth-centric bias. Planet M forces us to expand that filter. Life as we know it may be impossible on a diamond world. But life as we don't know it? On a crystalline surface bathed in pulsar radiation, with structured electromagnetic fields cycling every 2 hours? We genuinely don't know. And that uncertainty is the most exciting scientific statement you can make. A planet made of diamond. A dead star playing it like an instrument. Signals we can measure but can't fully explain. And a universe that keeps producing things our best models say are nearly impossible. Planet M isn't an anomaly. It's a preview. The cosmos is older, stranger, and more structured than we have any framework to describe. And every time we point a telescope somewhere new, it gets stranger. If this broke your brain a little, subscribe. We drop one of these every week. Next week, the void that shouldn't exist. A region of space 300 million light-years across, containing almost nothing. No stars. No galaxies. No dark matter. Just absence. Scientists call it the Boötes void. And the leading explanation is somehow more unsettling than the alternative. See you there.